Welcome to another Explainer. Today, we're taking some incredibly complex industrial concepts and turning them into clear, actionable knowledge. Now, if you're a power engineering student or a plant operator joining us, you already know that a modern power plant is an absolute marvel of interconnected systems. You've got your boilers, your massive turbines, your heat exchangers, the whole shebang. But today, we are going to focus entirely on a system that doesn't generate a single watt of power, yet completely dictates your legal right to operate. We're talking about environmental monitoring.
Okay, let's dive into this, because the macro stakes here are absolutely massive. In the modern industrial landscape, we are pushing hard toward an industry goal called zero effluent discharge. Basically, to comply with strict government regulations, power plants have a binding legal obligation to maintain incredibly low emission levels. We're talking about controlling thousands of chemical elements and compounds, pollutants that are often completely invisible to the naked eye. So, how do you measure something you can't even see? Well, it requires intense, long-term planning, continuous quantitative monitoring, and a seriously big budget.
Here is our quick roadmap for today. We'll cover the contaminant challenge, continuous emissions monitoring, extractive gas conditioning, opacity and transmissometers, the compliance data loop, and we'll wrap up with system failure troubleshooting. Starting right off with Section 1, the contaminant challenge and achieving zero effluent discharge.
So, the crucial point is that reaching zero effluent discharge isn't just about wastewater anymore, like we've seen historically in the pulp and paper industry. Power plants face the exact same legal pressure for their stack emissions. Take PM 2.5, for example. These are particles less than 2.5 microns in diameter. To put that in perspective, they are so unbelievably small they completely bypass the human respiratory defense system, penetrating deep into the lungs and contributing heavily to regional smog. These are the highly dangerous, invisible threats we absolutely must track to stay environmentally sustainable.
Moving right along to Section 2, Continuous Emissions Monitoring.
Enter CEMS, Continuous Emissions Monitoring Systems. And let's be clear, these are not optional. Every single plant has clearly defined limits for maximum allowable emissions, and CEMS is the system that continuously monitors, tracks, and reports these results directly to government agencies. CEMS regulations are built on three incredibly strict pillars. First, you have implementation rules, which identify the exact plant type and what compliance monitoring is required. Second, performance specifications, which dictate exactly how the equipment must be installed and certified. And third, stringent quality assurance requirements, ensuring the data is continuously accurate through regular preventative maintenance. Let's move to and see how this builds in Section 3, Extractive Gas Conditioning.
When you draw hot, dirty gas right out of a stack, you can't just feed it straight into a delicate chemical analyzer. It would destroy the equipment. It has to go through a very strict conditioning flow path first. Step 1 is often dilution with air, which essentially brings the gas down to a concentration the analyzer can actually read. Step 2 is cooling the sample gas down so we can safely handle it. Step 3 is scrubbing out the physical particulate matter so it doesn't clog up our sensors. And Step 4 is the removal of water vapor. Now, it is crucial to note for you operators out there that some advanced analyzers actually operate on a hot-wet basis. They are designed to handle extreme thermal environments and keep the gas heated well above the acid dew point, often around 150 degrees Celsius, which is roughly 300 degrees Fahrenheit. Because they run so hot, they can actually skip the cooling and water removal steps entirely.
Let's shift gears to Section 4, Opacity and Transmissometers. To understand why we sometimes use light instead of extracting physical gas samples, we really have to look at global standards. In Europe, the standard is to measure particulate mass directly, literally calculating milligrams per cubic meter of stack gas. But from a practical engineering standpoint, continuous direct measurement of particle concentration is incredibly difficult and super maintenance heavy. So, in North America, the standard practice is quite different. Because the technology to continuously and directly measure particulate mass is so challenging, North America relies on inferring that concentration by measuring something else entirely: stack opacity.
So what is it? Well, opacity is simply defined as the quantity of light that is lost as it moves through the stacked gases. Imagine a beam of pure light trying to cut across a dark, smoky stack. As it travels, that light hits entrained particles, like that PM 2.5 we talked about earlier. And it scatters, it's reflected, it's absorbed. Basically, the more particles floating in the gas, the more light gets lost. That specific percentage of lost light is your opacity, and it directly correlates to how much particulate matter you are pumping out into the atmosphere.
And this brilliantly illustrates exactly how we measure it. You have a light source, or a lamp, mounted directly on one side of the stack, and a detector aligned perfectly on the exact opposite side. The system measures the intensity of the light leaving the lamp, and then the detector measures the intensity of the light that actually survives the journey across the gap. The mathematical difference between those two intensities is your continuous opacity reading. Honestly, it's just really elegant optical engineering.
Pulling back to the macro view for Section 5, the compliance data loop. Okay, so you have your extractive gas analyzers reading chemistry and your optical transmissometers firing light beams. Together, they're generating thousands of data points a minute. What do you do with it all? Well, that raw data is fed directly into mathematical models for reporting to environmental agencies. Two very common models you'll see are 3-hour block averages and 3-hour rolling averages. A block average calculates your emissions in static 3-hour chunks, say midnight to 3 a.m., and then 3 a.m. to 6 a.m. Pretty straightforward. But a rolling average constantly updates. Every new hour or minute that passes drops the oldest data point and adds the newest, creating a really smooth, continuous, overlapping trend line.
So, why does this distinction actually matter to a power engineer in the control room? Because power plants are dynamic, highly volatile beasts. Upsets happen, right? Equipment temporarily malfunctions. If regulators looked at pure, instantaneous data, every minor hiccup would trigger a massive compliance violation. Rolling averages are fundamentally integrated right into the boiler control loops to give operators a realistic window. They smooth out the data, heavily preventing nuisance alarms and buying the control room crucial time to correct a temporary malfunction and bring those stack emissions back under control without breaching their license.
Wrapping things up with Section 6, System Failure Troubleshooting.
Now, what's really interesting about this is that perfectly balanced 100. It represents perfect system availability. The SEAMS equipment is incredibly tough, sure, but it's operating in a harsh, corrosive environment. When the monitoring equipment breaks down, you need to know that environmental monitoring has a strictly defined legal minimum availability. The formula is the total operating hours where the system provided quality-assured data, divided by the total plant operating hours, multiplied by 100 to get a percentage. Simply put, if your boiler is running, your SEAMS better be running and providing verified data. If it's not, from a strict regulatory standpoint, you essentially have zero environmental monitoring.
And here is the ultimate trap for operators. The system doesn't need to completely power down or explode to be considered failed. If a SIM sensor experiences a calibration error, or if the calibration drift is excessive, you are in major trouble. Specifically, if an analyzer's drift exceeds twice the amount allowed in its performance specification, the system is officially classified as out of control. At that exact moment, the data it produces is completely invalid. If this drops your system availability below the legal minimum, you are out of compliance, period. It is an immediate license violation, treated exactly the same under the law as if you had spewed toxic gas right over the limit.
To prevent this kind of catastrophic legal failure, control rooms rely on a massive web of alerts. Immediate problems, like an analyzer pump suddenly failing, a sample line clogging up, or a core computer crashing, trigger urgent alarms demanding instant operator intervention. Meanwhile, continuous data reviews highlight those slow, sneaky, long-term problems, like a steady sensor drift. This is exactly why routine preventative maintenance, like regularly scheduled calibrations and smoothly changing over redundant equipment, is absolutely vital to keep that data quality assured. So I want to leave you with this thought. As an operator or an engineer, it's incredibly easy to obsess over boiler temperatures, turbine RPMs, and your megawatt output. That's the exciting stuff. But if a single out-of-control SEAMS sensor or a slightly misaligned transmissometer can legally shut down your entire multi-million-dollar facility, you really have to shift your perspective. Environmental monitoring is not just some annoying side chore. It is the critical system that dictates your legal right to exist. Master the SEAMS, and you master the plant. Thanks so much for joining me on this explainer, and keep learning.